Hi there, I'm Shyan, and if you're interested in hearing about it, I'd be happy to tell you a little bit about work done by Virginia Vasilevska-Williams and myself on getting improved approximation algorithms for computing the longest common subsequence over small alphabets. To tell you about this problem, it will help to first establish some foundational definitions. The longest common subsequence problem is a fundamental string similarity measure, and here a string is just some sequence of characters from an alphabet. For example, the word online is a string from the English alphabet. A subsequence of a string is just a string formed by deleting some characters from that original string. For example, line is a subsequence of online, but the sequence of characters O, L, N, E also form a subsequence. Given two strings x and y, a common subsequence is just a string that is a subsequence for both x and y. For example, the word one is a common subsequence of the strings online and conference. The longest common subsequence, or LCS of x and y, is just the maximum length common subsequence between them. We'll use LCS of xy to denote the length of this longest common subsequence. Closely related to the LCS is the edit distance. Given strings x and y, the edit distance between x and y is just the minimum number of characters we need to delete from both x and y to recover the same string. We'll use ed of xy to denote this minimum number of deletions used to make the strings identical. It turns out that the deletions used in the edit distance recover a longest common subsequence for the input strings. Because of this, we have the following nice relationship between the LCS and edit distance. In particular, if we compute one of these measures exactly, we also know the exact value of the other measure as well. Now that we have those definitions out of the way, we can go ahead and talk more concretely about these problems. Using a classic dynamic programming approach, we can compute the LCS and edit distance of two length n strings in order n squared time, so quadratic time. It turns out that assuming the strong exponential time hypothesis, which is a popular conjecture in the field of fine-grained complexity, this is essentially the best we can do, in the sense that there is no truly subquadratic time algorithm for computing the LCS or edit distance. However, in practice, we often want to use LCS and edit distance computations on extremely long strings. For example, strings derived from DNA sequences. In these cases, it really is of interest to find algorithms that run in subquadratic time. Because of this, researchers are interested in seeing if we can get good approximations to these string similarity measures in better than quadratic time. For example, a C approximation to edit distance is just the task of finding a sequence of deletions that makes both input strings identical, such that the number of deletions used is no more than C times the minimum possible number of deletions. We're interested in particular in the case where C is a constant. For edit distance, there's been a lot of beautiful work in the past several years on getting better and better approximation ratios, from polynomial to polylogarithmic, finally culminating in a Fox 2018 paper by Chakraborty, Das, Goldenberg, Koki, and Sachs, which showed that it's possible to approximate edit distance to a constant factor in truly subquadratic time. Since then, there have been additional improvements, the latest of which is a work done by Andoni and Nosatsky, which shows how to get constant approximations in near linear time. That's the situation for edit distance, but in comparison, our understanding of constant factor approximation for computing the LCS is far more limited. In fact, we only know how to get constant approximations at all when the input string comes from an alphabet of fixed size. So here, given a parameter rho, we say a row approximation for LCS involves returning a common subsequence of two input strings, such that the length of this subsequence is at least a row fraction of the true LCS. So in other words, we want to return a common subsequence which is no more than a constant factor away from the true maximum length we could find. For LCS, there is a very simple algorithm which works by just returning the longest common unary subsequence for the purpose of approximation. And maybe it's easiest to see this by considering binary strings. So suppose we have two binary strings, meaning they only come from an alphabet where the symbols are 0 and 1. By counting how many times 0 appears in each string, we can find a maximum common subsequence that only uses zeros between the strings. The length of this string by construction must be at least as large as the number of zeros in the LCS. We can do the same for the symbol 1 and find a string whose length is at least as large as the number of 1s in the LCS. Consequently, the sum of the sizes of these two unary subsequences is greater than or equal to the length of the LCS. In particular, at least one of these unary subsequences has length at least half the LCS. So for binary strings, returning the longest common unary subsequence is guaranteed to be a half approximation. More generally, the same reasoning shows that if the strings come from an alphabet of size s, returning the longest common unary subsequence yields a 1 over s approximation to the LCS. Note that we can compute the longest common unary subsequence in linear time just by scanning the strings and counting how many times each character appears. Amazingly, despite the simplicity of this algorithm, it actually remains the best known LCS approximation algorithm that applies in general to all strings. Quite recently, Aviad, Rubinstein, and Zhao Song showed in a 2020 SOTA paper that in some special cases, it is possible, however, to get a better approximation. Specifically, they showed that for binary strings of equal length, we can get a better than half approximation in truly subquadratic time. We'll go into some of the ideas of the proof of this result a bit later in the talk. For now, I'll just note that one of the major insights was that in certain settings for certain types of strings, it's possible to use edit distance approximation to get better LCS approximation. This is a very cool result, and it's the first algorithm to beat the unary algorithm in any interesting setting for the purpose of approximation. However, it has two key limitations. First, it only applies to strings over an alphabet of size 2, and second, it requires the input strings to have equal length. So prior to our current work, this was the state of the art, and with this context set, I'm now ready to tell you how our new results take some steps in addressing these limitations. Our first result states that if there is a better than 1/2 approximation algorithm for LCS on binary strings, then for strings from any alphabet of size s, there is a better than 1 over s approximation algorithm for the LCS. In other words, if we could just overcome this equal length limitation for LCS approximation, even in the case of binary strings, we would have better approximation algorithms over all constant alphabet sizes, and finally beat the long-standing unary algorithm. The proof of this result is just a nice reduction from approximate LCS on larger alphabets to approximate LCS on binary alphabets, and we'll get into it later. Our second result states that for equal length strings from an alphabet of size s, we can compute a better than 1 over s approximation for the LCS in truly subquadratic time. In other words, we show how to extend Rubinstein and Song's result to hold not just for binary strings, but for strings from any constant size alphabet. Just like in our other result, the equal length limitation is the only barrier that remains. And this is comparing our current result to Rubinstein and Song's earlier result. So we'll now explore these results in a bit more depth. Our first result is a reduction from LCS approximation on strings from an alphabet of size s to LCS approximation on strings from an alphabet of size 2. And the proof uses this idea of alphabet restrictions, which we'll define now. Suppose we have a string over some alphabet. I have an example here. Then a subalphabet is just any subset of the characters of the full alphabet. And the restriction of the original string to the subalphabet is just the subsequence we get by keeping characters from the subalphabet while removing all other characters. So formally, here's the definition of that. So to prove this first result, suppose we have a better than 1/2 approximation algorithm for LCS on binary strings, and consider any two strings from an alphabet of size s. We consider every sub-alphabet of size 2 of the full alphabet, and then consider restrictions to these sub-alphabets. For each of the resulting restrictions, we just use our better than half approximation algorithm to get an approximate LCS value. We then return the largest of these common subsequences as our overall approximation. And this is the entire reduction from LCS approximation on alphabet of size s to LCS approximation on alphabet of size 2. Why does this approach work? Well, if we consider the two most frequent characters in the true LCS, together they make up at least a 2 over s fraction of the characters in the LCS, because there are only s characters in the alphabet. Then a better than half approximation for the subalphabet that contains these two most frequent characters will recover a better than 1 over s approximation for the full LCS. And that sketches the main idea behind this first result. For the rest of this talk, we'll hint at some of the ideas behind the proof of our second result. To remind us, this result states that for every positive integer s, we can compute a better than 1 over s approximation for the LCS of two equal length strings from alphabets of size s in truly subquadratic time. Rubinstein and Song already proved this sort of result for binary alphabets, and our improvement is to extend it for strings coming from potentially larger alphabets. So we'll first sketch some of the ideas used by Rubinstein and Song in the binary case, and then we'll briefly mention the additional insights that allow us to break the 1 over s barrier for all alphabets of size s. The improved LCS approximation algorithm for binary strings considers two main cases. In the first case, we assume we have two length n binary strings, which are balanced in the sense that they have about equal numbers of zeros and ones. For example, they're both equal to about n over 2. In this case, the longest common unary subsequence must be at least n over 2. So if the LCS is small, in the sense that it is much smaller than n, then this unary subsequence will already yield a better than half approximation. So we can handle the case when LCS is small and the strings are balanced. So let's instead assume the LCS is large. And intuitively, we can think of this as saying the LCS is close to the full length n. Then, in this setting, because of our earlier connection between the LCS and edit distance, the edit distance must be quite small. From this equation and our assumption on the LCS, we get that the edit distance is a very small fraction of the maximum possible length. If the edit distance is small enough, then a constant factor approximation to the edit distance will also be very small. This approximation will then give a small number of deletions, which when applied to the input strings yields a common subsequence. Because the number of deletions is so small, intuitively the remaining common subsequence is very large, and for appropriate settings of small and large in terms of certain parameters, this procedure will actually give a better than half approximation again. So this is the main idea behind how we get better than half approximations for balanced strings in this binary case. But one question we should maybe ask ourselves is, where did we actually ever use the fact that the strings have equal length? Because this condition turns out to be very important for this argument. And it turns out that we need this equal length condition in this step, where we claim that if the LCS is large, so is the edit distance. So note that the LCS of two strings is always at most the length of the smaller string, because it must be a common subsequence for both. And the edit distance must be at least a difference in the lengths between the two strings, since we must delete enough characters from the larger string to become at least at most the size of the smaller string. So when the strings have very different length, just because the LCS is large does not mean that the edit distance is small in any interesting sense. This is the main reason the equal length condition seems important. It's only in this setting where we have a way of getting improved approximations for the LCS of balanced strings using this edit distance approximation approach. If we could find a different way to handle this balanced case, then it's possible that we could avoid this equal length condition altogether, but so far it's not clear how to do this. All right, so far we've considered the balanced case of this LCS approximation algorithm, and it remains to handle the case of imbalanced strings. So this case is much more technically involved, and we won't go into very much detail at all about the arguments here. At a very high level, they split the string into its left and right ends and a middle portion. The location of these splits depends on the frequencies of zeros and ones in the input strings. We then look within segments and check frequencies of zeros and ones within each segment. And if two segments have consistent frequencies, then we can use the unary algorithm to find a large common subsequence. For example, if the left ends of both strings have many more zeros than ones, then just looking for a common subsequence of all zeros from those parts of the strings will intuitively be useful for the purpose of approximating the LCS. And then we can use some method on the rest of the strings. It could also be the case that corresponding parts of the strings are balanced. In this case, we can also, again, pair those parts up and then just use the edit distance approximation method from the balanced case to get a good approximation for part of the LCS. And then the full algorithm essentially combines these two methods, the unary algorithm and edit distance approximation, on different parts of these strings to get a good approximation to the LCS overall. But the details of this involve somewhat intensive casework analysis, intensive frequency analysis. So that summarizes at a very high level the proof structure for this improved binary LCS approximation. Now, how can we extend this result to alphabets of size greater than 2? At a very high level, there are two initial cases to consider. First, the case of balanced strings. This is analogous to what was done in the binary case. Second, we have a new case, which is the case where the true LCS of the strings is not balanced. And then if we do not fall into either of these cases, it turns out we can use a special sort of sub-alphabet restriction algorithm, similar to the one used in the proof of our first theorem, to reduce the problem, this approximation algorithm, to an LCS approximation algorithm on strings from a binary alphabet. So like I mentioned, the first case that we're considering here of balanced input strings is just analogous to the argument used in Rubinstein and Song's algorithm. We just use constant factor edit distance approximation algorithms again, and because these algorithms work independent of the alphabet size, we have no issues extending it here. So let's focus on the second case of an imbalanced longest common subsequence. Given two strings over an alphabet of size s whose LCS is not balanced, here by being not balanced, we mean that some character accounts for a noticeably larger than 1 over s fraction of the symbols in the string. In this setting, returning a unary common subsequence just consisting of this most common character in the LCS will already be better than a 1 over s approximation to the LCS. So again, the unary algorithm will give us better than 1 over s approximation in this case. So this is an easy case. So now suppose we do not fall into either of these easy cases of balanced strings or imbalanced LCS. Then we have two strings that are not balanced, but their LCS is balanced. If their LCS is balanced, this means that every character from the alphabet appears about the same proportion of the time in the LCS. Yeah, in the actual details of this proof, this involves some parameter choice, but we'll just keep things intuitive. So consider any binary sub-alphabet of the full alphabet. Let x be the restriction of a to this sub-alphabet and y be the restriction of b to the sub-alphabet. Because the LCS is balanced, a better than half approximation for the LCS of x and y will recover a better than 1 over s approximation for the LCS of a and b. Intuitively, this is because the two characters in our binary sub-alphabet will account for about 2 over s fraction of the LCS. And then if we compose this with a better than half approximation, we'll get a better than 1 over s approximation overall. So this is one of the major insights in our work. We consider frequencies of characters in the LCS as well, not just the input strings, and then exploit the behavior there. We can then combine this idea with the idea of picking this binary sub-alphabet very carefully instead of just arbitrarily, so that the new restricted strings x and y have some very nice structure. In particular, it turns out that we can force x and y to satisfy some rather strict frequency conditions, and leveraging these frequency conditions with the ideas of the string partitioning method of Rubinstein and Song's previous algorithm lets us get a better than half approximation for the LCS of x and y. It's worth noting that x and y here might have very different lengths, which is why this step here is somewhat non-trivial. We really are exploiting some extra structure in x and y, namely the special frequency condition, which we won't go into detail today, but is detailed in our paper, that lets us get around this equal length restriction. If we could handle equal length strings along with some other frequency without this frequency condition, then by our first theorem, we have already got an improvement for all alphabet sizes. All right, so that finishes the main idea of our results. To summarize what we discussed in this talk, we overviewed some of the ideas behind the better than half approximation algorithm for LCS of equal length binary strings. Then we discussed two new results from our work. First, we showed that to get better LCS approximation algorithms for all alphabets, it just suffices to get better LCS approximation algorithms in general over binary alphabets. Second, we showed that for equal length strings, we can get a better than 1 over s approximation algorithm for the LCS over alphabets of size s for any fixed positive integer s. The ideas used in our proof combined existing approximation algorithms for edit distance, some sub-alphabet restriction techniques, and some ideas exploiting character frequency balance and imbalance in strings. There still remains many interesting open problems in this area. The most immediate ones given our work here is, can you get rid of this equal length assumption? Because of our first theorem, answering this question, to answer this question, it suffices to just answer it for the case of binary strings. It will also be very interesting to see if we can get better approximation ratios in general for these algorithms. Our approximation ratios are quite modest improvements over the unary subsequence, approximation ratio of the unary subsequence algorithm. And it would be interesting to see if either we can get just better approximation ratios in terms of absolute quantity, or some better dependence in terms of the alphabet size, for example. In any case, I hope this talk got you a little bit more excited about the longest common subsequence approximation problems, and that you got some helpful context for some of the new results in this area. Thank you.